Of all the worlds in our solar system, only one is confirmed to support life. That world is Earth. From space, it appears as a brilliant blue sphere, glowing softly against the vast darkness of the cosmos. Its surface is dominated by enormous liquid oceans that stretch across more than 70% of the planet. Above those oceans hangs an oxygen-rich atmosphere, carefully balanced to sustain countless living organisms. Beneath the surface, powerful geological forces constantly reshape the land, driving volcanoes, earthquakes, and mountain ranges upward over millions of years. Deep within the planet, a churning iron core generates a powerful magnetic field that shields all life from harmful solar radiation. No other planet we have yet discovered combines all these features so perfectly. Earth is not merely a rock orbiting a star. It is a rare, dynamic, and extraordinarily complex world, and its story is far more surprising than most people ever realize. Now, while Earth looks perfectly round from space, that is actually a beautiful illusion. Our planet is not a true sphere at all. It is what scientists call an oblate spheroid, meaning it is slightly flattened at the poles and bulges outward around the equator. This happens because Earth is constantly spinning, and that rotation pushes mass outward along the middle. The equatorial diameter is actually about 43 kilometers greater than the polar diameter. It is a subtle difference, but a real one. And this shape leads to one of geography's most surprising revelations. Most people assume Mount Everest is the point furthest from Earth's center, given it is the tallest mountain above sea level. But that title actually belongs to Mount Chimborazo in Ecuador. Because it sits so close to the equatorial bulge, its peak extends further from Earth's core than Everest ever reaches. Now, long before satellites or modern instruments, ancient thinkers were already piecing together the true nature of our world. Journey back more than 2,000 years to ancient Greece, where philosophers had already concluded that Earth was not flat but spherical. This was remarkable reasoning for its time, built purely on careful observation and logical thinking. Around 240 before the Common Era, a Greek scholar named Eratosthenes took this understanding even further. Working in Egypt, he noticed something fascinating. In the city of Syene, sunlight fell perfectly straight into deep wells during midsummer. Yet in Alexandria, located further north, vertical sticks cast measurable shadows at the exact same moment. Using basic geometry, Eratosthenes calculated the angle between these two cities and extrapolated Earth's full circumference. His result was astonishingly close to what modern measurements confirm today. All of this achieved without any technology beyond shadows, sticks, and brilliant mathematical reasoning. Building on those ancient Greek foundations, the 16th and 17th centuries brought an even more dramatic shift in understanding. For centuries, most people believed Earth sat motionless at the center of everything, with the sun, moon, and stars revolving around it. Then came Nicholas Copernicus, who in 1543 proposed a radical alternative. Earth and the other planets actually orbit the sun. This heliocentric model was deeply controversial, challenging centuries of religious and philosophical tradition. Johannes Kepler refined the idea further, demonstrating through precise mathematics that planetary orbits are elliptical rather than perfectly circular. Then Galileo Galilei pointed his telescope skyward, gathering direct observational evidence supporting the heliocentric model. Together, these three visionaries dismantled humanity's assumption that we occupied a privileged, central position in the universe. Earth was suddenly just one world among many, circling an ordinary star. That humbling realization permanently transformed science, philosophy, and our understanding of where we truly belong in the vast cosmos. Earth holds a special position as the third planet from the Sun, and one of 4 rocky terrestrial planets in our solar system, alongside Mercury, Venus, and Mars. Unlike the gas giants further out, Earth has a solid surface shaped by geology, water, and life. But Earth's path around the Sun is not a perfect circle. It follows a slightly elliptical orbit, meaning the distance between Earth and the Sun changes throughout the year. At perihelion, occurring around January 3rd, Earth sits closest to the Sun at roughly 147 million kilometers away. At aphelion, around July 4th, it reaches its farthest point at about 152 million kilometers. One complete orbit takes approximately 365.25 days. That extra quarter day adds up over 4 years, creating a full extra day. This is precisely why we add a leap day every 4 years, keeping our calendars aligned with Earth's actual journey around the Sun. Now that we understand Earth's orbit, let's talk about something equally fascinating: rotation. Earth completes one full spin roughly every 23 hours and 56 minutes. This is called a sidereal day, measured against the distant stars. But our standard solar day lasts exactly 24 hours. So where do those extra 4 minutes come from? The answer lies in Earth's orbital journey around the Sun. As our planet rotates, it also moves forward along its orbit. By the time Earth completes one full spin relative to the stars, it has shifted slightly in its path. The Sun now appears at a slightly different angle in the sky. To bring the Sun back to the same position overhead, Earth must rotate just a little bit more. That small extra rotation accounts for the 4-minute difference. It seems minor, but without this distinction, our clocks and calendars would slowly drift out of alignment with the actual position of the Sun. Building on what we just explored about Earth's rotation, here is something even more remarkable. Earth's spin is not constant. It is actually slowing down, very gradually, over millions of years. The culprit is the Moon. Through tidal interactions, the Moon's gravitational pull creates a gentle but persistent braking effect on Earth's rotation, causing each day to grow slightly longer over vast stretches of time. This means ancient Earth once spun considerably faster. Scientists studying fossil records and ancient coral growth patterns estimate that roughly 500 million years ago, a single day lasted only about 22 hours. Even further back, early Earth may have completed a full rotation in just around 6 hours. With shorter days, there were also far more of them in a single year. Ancient Earth may have experienced over 400 days annually. It was a faster, more energetic world, dramatically different from the familiar planet we inhabit today. Now, speaking of Earth's rotation and its quirks, let's talk about something that affects every single one of us throughout the year: the changing seasons. Earth doesn't sit perfectly upright as it orbits the Sun. Instead, it leans at an angle of 23.5 degrees. This tilt is the true reason we experience spring, summer, autumn, and winter. Here's where a very common misconception needs clearing up. Many people assume seasons happen because Earth moves closer to or farther from the Sun during its orbit. But that's simply not the case. In fact, Earth is actually slightly closer to the Sun during the Northern Hemisphere's winter. What truly drives seasonal change is the angle at which sunlight strikes Earth's surface and how many hours of daylight each region receives. When the Northern Hemisphere tilts toward the Sun, sunlight arrives more directly and days grow longer, creating summer. When it tilts away, sunlight spreads more thinly and days shorten, bringing winter. If you photographed the Sun at the same time every day for an entire year, something remarkable would appear in the sky. The Sun would trace a distinctive figure-8 pattern called the analemma. This curious shape emerges from the combination of Earth's axial tilt and its slightly elliptical orbit, causing the Sun to appear higher or lower and slightly ahead or behind its expected position throughout the year. Ancient astronomers noticed this pattern, and today it remains one of the most visually striking demonstrations of Earth's complex motion through space. Now, surrounding this dynamic planet is an atmosphere that makes everything possible. Stretching hundreds of kilometers above the surface, it is composed of roughly 78% nitrogen and 21% oxygen. The remaining 1% includes argon, carbon dioxide, water vapor, and various trace gases. Each component plays a unique role in supporting life, regulating temperature, and shaping the weather systems that constantly move across our world. Sitting roughly 15 to 35 kilometers above the surface, the ozone layer acts as Earth's invisible shield, absorbing the vast majority of the Sun's dangerous ultraviolet radiation. Without this protective barrier, life on land would be virtually impossible. Ultraviolet rays damage DNA, destroy cellular structures, and make exposed surfaces hostile to nearly all living organisms. The ozone layer transformed barren continents into habitable environments, allowing complex life to eventually crawl out of the oceans and colonize the land. Equally important are greenhouse gases, including carbon dioxide, methane, and water vapor, which trap heat radiating from Earth's surface. Without this natural warming effect, global temperatures would plunge far below freezing, turning our vibrant world into a frozen wasteland. Together, The ozone layer and greenhouse gases create a finely balanced atmospheric system that has sustained diverse ecosystems and supported the extraordinary web of life developing across billions of years of planetary history. Earth's water is never still. It moves through an immense planetary system in a continuous, endless journey. Heat from the sun causes water to evaporate from oceans, lakes, and rivers, rising invisibly into the atmosphere. As it climbs higher into cooler air, it condenses around tiny particles, forming clouds that drift across continents and coastlines. Eventually, that moisture falls as rain or snow, feeding rivers, replenishing glaciers, and soaking into the ground before flowing back toward the sea. At the heart of this cycle sit Earth's oceans, covering roughly 71% of the planet's surface. These vast bodies of water do far more than hold moisture. They absorb enormous amounts of heat from the sun, regulating global temperatures and stabilizing climate patterns across entire hemispheres. They also absorb significant quantities of carbon dioxide, slowing atmospheric buildup. Beneath their waves, oceans shelter extraordinary biodiversity, hosting ecosystems of breathtaking complexity and richness found nowhere else on Earth. Here is a thought that truly puts Earth's oceans into perspective. If every mountain were flattened and every ocean trench filled in, leaving Earth's surface perfectly smooth, the entire planet would vanish beneath a global ocean almost 3 kilometers deep. That is how much water our world actually holds. But of course, Earth is anything but smooth. Beneath your feet, the planet is restless and alive. Earth's outer shell is broken into roughly 15 major tectonic plates, massive slabs of rock that float atop the semi-molten mantle below. These plates are constantly moving, grinding past each other, colliding and pulling apart. Where they collide, mountain ranges rise. Where they separate, new ocean floor is born. Where one plate dives beneath another, deep ocean trenches form and volcanoes erupt. Earthquakes shake the surface as these enormous forces release energy. This dynamic system has been reshaping our planet for billions of years. This constant tectonic activity does far more than reshape mountains and open ocean basins. It acts as a planetary recycling system, drawing carbon dioxide from the atmosphere through weathering, locking it into rocks, and then releasing it again through volcanic eruptions over millions of years. Scientists call this the carbon silicate cycle, and it functions like a long-term thermostat for Earth's climate, preventing temperatures from drifting too far in either direction over geological timescales. Without this geological engine running beneath our feet, carbon dioxide levels could spiral out of control, potentially turning Earth into a frozen wasteland or a scorching greenhouse world. Volcanic activity also enriches soils with minerals, creating some of the most fertile land on the planet. Many researchers now believe that active plate tectonics may not simply be a feature of Earth, but rather a fundamental requirement for any world hoping to sustain complex life across billions of years. Beneath the tectonic activity lies an even more extraordinary feature: Earth's interior. At the very center of our planet sits a dense core composed primarily of iron and nickel. The outer core remains molten, with temperatures reaching thousands of degrees. As this liquid metal churns and flows, driven by heat and Earth's rotation, it generates electric currents that produce a vast and powerful magnetic field surrounding the entire planet. This magnetic field, known as the magnetosphere, extends far into space, acting as an invisible shield. Without it, the solar wind, a constant stream of charged particles blasting outward from the sun, would gradually strip away Earth's atmosphere over millions of years. Mars, which lost its magnetic field long ago, suffered exactly this fate, leaving it barren and exposed. Earth's magnetic shield preserves the atmosphere, protects surface life from harmful radiation, and maintains the delicate conditions that make our world so remarkably habitable. As charged particles stream outward from the sun in what we call the solar wind, Earth's magnetic field does something remarkable. Rather than allowing these high-energy particles to bombard our atmosphere directly, the magnetic field funnels them toward the polar regions, channeling their energy into one of nature's most breathtaking displays. When these charged particles collide with gas molecules high in the atmosphere, they transfer enormous energy, causing those molecules to become excited. Oxygen atoms, sitting roughly 100 kilometers above the surface, absorb this energy and release it as light. The most common result is a vivid green glow, the signature color of excited oxygen atoms returning to their natural state. This is the aurora borealis in the north and aurora australis in the south, shimmering curtains of green, occasionally purple and red, dancing silently across polar skies. Without Earth's magnetic field faithfully deflecting the solar wind, these dazzling light shows would simply never exist. Among all the moons in our solar system, Earth's moon stands out as unusually large relative to its host planet. Its diameter is roughly 1/4 that of Earth, making it a giant companion by any measure. This immense gravitational presence drives the rhythmic rise and fall of ocean tides, which have shaped coastlines, influenced marine ecosystems, and even affected early biological evolution over billions of years. But the moon's influence goes far deeper than tides. Scientists believe the moon acts as a gravitational anchor, stabilizing Earth's axial tilt at roughly 23.5 degrees over vast stretches of time. Without this stabilizing force, Earth's tilt could shift dramatically and unpredictably, triggering extreme climate swings that might have prevented complex life from ever gaining a foothold. Some researchers suggest this remarkable stability was not just helpful, but perhaps essential, providing the consistent, livable conditions that allowed advanced life and eventually human civilization to emerge and flourish across our extraordinary planet. When astronauts first gazed back at Earth from space, everything changed. That iconic image, a small blue marble suspended in absolute darkness, revealed something profound. Our world looked fragile, beautiful, and deeply precious. No borders, no divisions, just one interconnected living planet. Modern space exploration has deepened this perspective enormously. Missions across our solar system have shown us barren, hostile worlds, reinforcing just how extraordinary Earth truly is. Then came exoplanet research. Scientists have now confirmed thousands of planets orbiting distant stars. Yet finding worlds with liquid water, breathable atmospheres, stable temperatures, and active geology appears remarkably difficult. The precise combination of conditions Earth enjoys, the right distance from the right star, a protective magnetic field, a large stabilizing moon, seems extraordinarily rare. The Kepler Space Telescope surveyed over 150,000 stars. Truly Earth-like candidates remain vanishingly few. Our planet may not simply be special to us. It may be genuinely exceptional across the entire universe. And yet, for all we have learned, Earth still guards its deepest secrets. The ocean floors remain largely unmapped, the atmosphere continues to surprise researchers, and the forces churning far beneath our feet are still not fully understood. Centuries of discovery have answered extraordinary questions, but each answer seems to open entirely new ones. The story of our planet is not finished. It is still being written, layer by layer, discovery by discovery. In many ways, understanding Earth is not just about knowing our home. It is about understanding what makes life possible, anywhere in the universe, and perhaps grasping our true place among the stars. Every mystery solved brings us closer to those profound answers. If you found this journey through our remarkable world as fascinating as we did, make sure you watch the next video and subscribe so you never miss what we explore next. The cosmos is waiting.